Okay, so I'll start the lecture then. So we are continuing our discussion of diagrams, and hopefully today we'll get to the point where we can reproduce many of the things we've learned in the course so far of using diagrams, and then maybe even very quickly do a bit more and learn a few new things. But before I get started, there was a question last time by Jonah, I believe, on the KMS periodicity, and I kind of mumbled how the proof should go. But let me just display it rather explicitly because it's not that complicated, and I really should have displayed it even earlier. So we're considering, imaginary time Green's functions like this, where A and B are any operators. This is the definition where the time evolution everywhere is just the full Heisenberg time evolution, the full Hamiltonian without going into the interaction representation. This is how the operators all evolve. So that's the definition, which, once you put in the full Hamiltonian, can be written as this. And then, of course, to generate diagrams, you can't do anything with this. To generate diagrams, you have to go to the interaction representation and then expand in powers of the interaction. But to prove the KMS theorem, actually, it's much easier to just start with this basic definition. So let's just start from that definition and see the KMS theorem. So I'm going to assume, which again, something you can prove from that definition, that the Green's function is only a function of time differences. So I'll put tau prime equal to 0. You can put it non-zero if you want, just a little bit more complicated. And let's assume tau is at this interval, the lower half of the fundamental interval between minus beta and 0. Then the 2-point correlator, because now tau is negative, has A of tau first and B, which is now at tau prime equals 0, so it's just B of 0. And this is, since you've reversed the operators, if these were fermionic operators, that would be a plus sign. And if these were bosonic operator, you'd have the original minus sign. Okay, so let's just write this out in terms of the full Hamiltonian. Is the expectation value in the full Hamiltonian of e to the minus beta h at temperature beta, inverse temperature beta. Then B is just B. And the Heisenberg representation of A of tau is right here. So that's the expression. Okay. Now let's evaluate the other one. Let's shift tau by beta. But now tau plus beta is positive because of the constraint on tau here. And therefore, A of tau plus beta becomes later than B of 0. So now we have to put B of 0 first and then A. All right, and now we just write down the definition of the expectation value. It's the trace of e to the minus beta h of A of tau plus beta, which is this and this times A in the usual Heisenberg time evolution, and then B at time 0, which is just the B in the Schrodinger representation. Okay, so this is what we get. And this is not obviously equal to this, but with a very simple manipulation, you can see it is. So what we're going to use is the basic property of the cyclicity of the trace. That's all we need. So we can take the B from the last operator and make it the first operator. And then we can split this up into e to the minus tau h and e to the minus beta h. And let's just take e to the minus beta h and also move that after moving B to over here. So when you do that, you get an e to the minus beta h times B, and the e to the minus tau h is still left over. And then because h commutes with itself, and that we also use that property here, we can just combine these two and make that e to the tau h. And then you're done. Now you can see this expression is basically exactly that expression. And hence the anti-periodicity or periodicity of this Green's function. So, I mean, the basic thing to remember is it just comes from the cyclicity of the trace. And the origin of the e to the minus beta h is different. Here, the beta comes from the thermal evaluation. Whereas here, that thermal beta just disappear, but there's another beta that comes from the time evolution of A, which also has the same factor of beta, and that's what becomes the density matrix. So it's a bit of a trick, and we're just using the fact that the time evolution operator and the density matrix are the same operator, and that what gives you the anti-periodicity. Time evolution for time beta. All right, so that's then the proof of the KMS condition. Let me also recall the basic rules for the Findment diagrams, which we're now going to evaluate willy-nilly in this lecture. Where's the rules? I had them written down at some point. Yeah, here we go. So these are the rules from the textbook. When I'm following basically exactly these rules with the small changes in notation. So this is the propagator of a free fermion. Comes from the contraction, it's G0 at momentum K, and frequency, I tend to call it omega n, and the book calls it Kn. Then there's an interaction line, which also will be carrying frequency and momentum. I've called it V of Q, the book calls it W of Q. And there's a negative sign associated with that for repulsive interaction. And then the rules, you have to conserve spin and form momentum at each vertex, just like Kirchhoff's laws. And then you have to just draw all topologically distinct diagrams with two external fermion lines and lots of as many interaction lines as you want, and then internal fermion lines, and all the internal momenta and frequencies have to be summed or integrated over. And there's really, once as you keep them topologically different, that's it. You don't have to keep track of any other numerical factors, all the 1 over n factorials and 1/2 to the 2 to the power n. That just cancel out or by the multiplicity of the relabelings. The only tricky factor is the -1 to the f, where f the number of fermion loops. And then there's convergence factor, which we discussed for just two diagrams, the one that involved having the same time at the ends of just a single loop, the tadpole diagram. Okay, so that's it. Those are the rules, and from this we can now, in principle, generate perturbation theory to infinite order. Okay. Any questions so far on the rules? Oh, yeah, okay. Still in that chapter, we also introduced the concept of one-particle irreducible diagrams. Those are diagrams that cannot be cut into two pieces by cutting an electron line, not an interaction line. So these are irreducible, and these are reducible because they fall apart when you cut them there. And then the sum of the one-particle reducible diagrams is called the self-energy, sigma, with the external legs truncated. So the external G0s are not included, that you explicitly include in this Dyson series. So any Green's function can be written as G0, G0 sigma G0, and so on to infinite order. And this is just a simple geometric series which you can resum to get the famous Dyson's equations that G inverse equals G0 inverse minus sigma. So that reduces the work to just summing one-particle irreducible diagrams, and this is the series for sigma. And then you can even reduce the work further, although that's, it does take some work then to implement that. If you take these equations and replace the internal lines by full lines, so you have full Green's function G, write that as a full line, then you replace the internal line by a full line. You can check that you're not double counting by doing that, and then you get the Hartree-Fock equations. So proving that these are the same as the Hartree-Fock equations we had before, I don't know. That's a bit of a mess, but it's not that difficult a principle. I think it's worked out in some detail in Feder and Velechka. I'll probably just copy those notes in Feder and Velechka and put them on the website. Okay. So that's the summary where we were. Questions? Okay, and then let's actually get some numbers. And what we evaluated last time was G0, the time-ordered Green's function of free electrons. And what we got was a very simple expression, at least after a Fourier transform. It's, I don't know why I wrote an arrow there. It should be an exclamation point. Okay. This is it. So it's I omega n minus Ek, where omega n is the so-called Matsubara frequency, which is equal to, for fermions, the odd multiples of pi times temperature. All right, so now you know all the rules, and now it's just a matter of implementing them and doing many integrals and summations and so on. Okay, so let's do a few. So let's evaluate. So these are the same statements here. Let's evaluate the very first term in the electron Green's function, which involves an interaction. Okay, this, as we'll see, is, and that becomes quite evident, is the same as the Hartree term. And the Hartree term actually for the electron gas we threw out because it canceled against the uniform positive background. But we don't want to deal with that complexity here. So let's imagine we're talking about helium-3, which has a short-range interaction, and it's not a Coulomb gas, it's just some short-range repulsive interaction, and there's some V of Q, which is still, and V of 0 is finite. Okay, so then what would this diagram be? Okay, you have the two external legs, and that will give you this term here. Then you have a factor of minus V from the rules. You have a factor of -1 from the fact that there's a closed fermion loop. So there's a closed fermion loop, gives you an extra -1. The 1/2 and the 2 don't, well, what happened there? Yeah, so the 1/2 gets canceled by multiplicity. So let me just erase that 1/2. That shouldn't be there. Okay, and then there's a factor of 2 that comes from the sum of the spins. So there was a rule that, so this thing can have, if this line has some spin sigma, that spin gets preserved, but the sigma prime can be anything. It's a total free. So there's a sum over sigma prime that gives you a factor of 2. So that gives you this factor of 2. Okay, you pull all that first. And actually this, if you're evaluating the self energy, you would just drop this term. This wouldn't be there in the self energy, and the rest would be whatever it is. Okay. All right, so now we have to do the sum over Q and the sum over this Matsubara frequency in here. And that sum is divergent. It's infinite. But this is not like a field theory infinity. Well, where you have to, do all kinds of renormalizations, so don't panic. Here, everything is finite because we're really talking about a non-relativistic gas. There is no infinite sea of antiparticles going off to negative energy that's going to give you all kinds of infinities. And the reason this infinity is there is because of this issue with time ordering and point splitting. So we always take a Hamiltonian with the side daggers come to the left of the size. And the rule is that you got to put this convergence factor. I just mentioned that rule to make sure that there's a side dagger and a psi here, side dagger created, and that the time of the side dagger is a bit earlier than the time of the psi. And if you look at the Fourier transform, what that means is you have to have this convergence factor. Okay, so once you put this tiny little factor with eta going to 0, in fact, the whole thing is convergent. So that's all it takes. That infinitesimal exponential is enough to make the whole thing convergent. All right, so what about this graph then? So this graph is almost exactly the same, except for two differences. One is that there's no fermion loop. So there's no fermion loop here, and therefore there's no extra minus sign. So here there were two minus signs, one from the fermion loop, one from the interaction. Here there is only the -1 from the interaction. And then the other difference is that there's no factor of 2 from the sum over spins. So here the spin sigma here continues to spin sigma, and then this is the same spin sigma. So whatever the spin of the internal line is the same as the spin of the external lines. And this is something that also happens in the Fock term. This is like the Fock term, where there's the spins of the, you only get exchange, the exchange interaction only happens between electrons of the same spin, because those are the ones that feel the Pauli exclusion principle. Other than that, it's exactly the same expression. And the V of, now the V here is sorry, it's not exactly the same expression. Now the momentum is a bit complicated. So here this was K, and so you said momentum Q went there, so there must be momentum K plus Q here, or coming in that way, sorry. So this K comes in, Q comes in, and gives you K plus Q. And then this is V of Q. So this gives you a V of Q here, and this is E of K plus Q. And it's in fact very much this term that we evaluated when we took this expression that we evaluated to get the Hartree-Fock quasi-particle energy. Here, momentum K keeps going through this way, and this is a circle. So in fact, this object here is carrying 0 momentum. That's why you had a V of 0. Okay. All right. So there's an integral to be carried out over momentum. There won't be any problem doing that. I mean, there is always a lattice, or in fact, in this case, we'll see that the integral is always convergent, even in the continuum. The only tricky part is how do you do the summation over epsilon. So that brings me to this. So this is the kind of thing you often have to do, where you have some summation over discrete frequencies omega n of some function of I omega n. So there's various ways of doing it. The foolproof way is the contour integration method, but it's a bit cumbersome, and it's hard to always get the signs right. What I prefer to use is to just evaluate this basic summation that I'm going to show you using the contour integration, which actually gives you a very simple answer, and then use partial fractions, as you'll see when I actually evaluate it. You can always reduce by using partial fraction everything to summations of this type. Okay, but let's just take the problem at hand. So where f is any arbitrary function. Okay, so what we're going to, and it's a function of I omega n. So what we're going to do now is consider the summation in the complex frequency plane, where this is the complex frequency plane, where z is I omega n. So what we have to do is evaluate sum of f of z at these points. These are the points where z is I omega n in the complex z plane. So I times pi t, 3i times pi t, 5i times pi t, and so on. For fermions, let's just do it for fermion. The same things can work for bosons. So the way you do this is you convert the summation to an integration on this contour C going this way and here. And you're assuming that the function f itself has no singularities on this line. So the C's can be arbitrarily close to the vertical imaginary axis. So what we're going to do is multiply f by another function, f, little f, so that little f has poles with residue 1 at exactly at these points. Okay, so you need a function of z, little f of z, whose poles are at these points? Well, in fact, we know such a function. It is precisely the Fermi function. So it's easy to check that this is exactly the function that does the trick. So this vanishes when this has a pole when e to the beta z is -1, and that's exactly when z is odd multiple of pi t. The residue you can work out is -1 over beta, so you have to put an extra factor of minus beta to compensate for that. So therefore, I can write this summation over frequencies as this integral on the contour C. So this, if I give you this function, if I give you this expression, and I tell you that f of z has no singularities on the imaginary axis, and I tell you the C is this contour, goes up to infinity this way and comes back this way, then easy to check by the method of residues that this expression is exactly equal to this expression. Okay, so far everything is formally completely well defined, provided, of course, these integrals don't blow up at plus or minus infinity. Okay, so this is the contour integration we want to evaluate. So now it reduces the problem of contour integration, which is a little easier. So now, what is this f of z? In both the Hartree and the Fock term, the f of z was something like this. This is f of z, this expression here. So let me just write it out. So now our f of z is equal to e to the z eta over z minus ek. Okay, so we just plug that into this expression, and I get this. I have to evaluate this expression. Okay, so now what we see is that the original contour was here, and we have to get the orientation right. Yeah, so we go anti-clockwise around the poles. Okay, so now if we close this contour on the poles inside, then we'll just get back to where we started from. So that's useless. So what we want to do is to take this contour and open it up the other side. So we want to take this contour and imagine closing it by going out to infinity this way. You want to go this way and this way. Okay, so we have to look for poles now in the rest of the complex plane of the other expression, the interesting expression that we want, which is this expression here. Okay. So now there's a, let's see, what am I going to say? I forgot. I'm a little bit, yeah. So the other thing we have to make sure of that if we are able to do this trickery, that whatever this function is, everything in here, better go to 0 fast enough at infinity along the real axis. So as we go out to infinity along the real axis, along this way, the contribution from this big contour should be 0. So we have to check that. And this is where this thing comes in to save the day. So if you go out to plus z going to infinity, no worries. This thing goes to 0 as e to the minus beta z when z is positive and real. And so you're fine, even without that factor. But on this side, this goes to, when z goes to minus infinity, that goes to 1. So there's a huge contribution here. But luckily, this goes to 0, provided eta is positive. And therefore, you're safe. So you really need that factor to get a finite answer. So then on this part, however, there's no other pole. The only pole is z equals ek. So this just gives you 0. So now you take this big contour and you shrink it down around this. And lo and behold, you get this, which is just the Fermi function. So that's wonderful. That tells us For example, if I look at the Hartree contribution, what is this equal to? So this is exactly what we evaluated. And so this tells me, if I write down the expression for the self-energy, sigma of, well, here I have some frequency coming in, which is omega and Ek, but it'll be independent of both. Sigma of omega n and Ek is equal to, you'll get 2 from the spins, V of 0 times sum over Q of just the Fermi function of EQ. Yeah, and that's nothing but the density. And that's, that's exactly right. That's the Hartree contribution. In the Hartree contribution, you remember you did things like this: C dagger, C, C, and you average this to get the correction. And what is this? It's just the Fermi function NF of Ek, where this was K and this is K. So that's all it is. You get all that hard work from contour integration and really fancy stuff. That's just the world's most complicated way of realizing that expectation value of C dagger C is equal to NF of Ek, something you already knew from freshman physics. So that's all this has done. All this fancy stuff with poles and contour integration has told you, gives you the right answer, exactly what you expected. Okay. All right. So questions. So we got the very first part of the course done by diagrams. Let's now look at the second part, where we looked at Kubo formula. So the Kubo formula we evaluated was our expression for the Kubo formula was the commutator of the density in real-time evolution, and then you had a theta function of time, and then you evaluated the expectation value of that. That was the Kubo formula. That's what we want, but it's not something that's easy to compute by using diagrams. What is easy to compute is this expression here. So I'm just going to put this expression down because it's a very natural way of generating diagrams. And then in a few minutes, we'll see how to get what we really want. So let me define the Green's function of two density operators. Okay, so you have, and I'm being sloppy, and I will just, all the interesting structure in the frequency and time domain. So the momentum I just, take as usual, and there should be a minus here, rho of Q and rho of minus Q. Okay, so you have a density operator at time tau and a density operator at time 0, and you want the time ordered expectation value. So that's how you define chi of Q and omega is the time ordered correlation, Green's function of two density operators, rather than a C dagger and C, it's the density. Okay. Because by the rules we have developed, there's no problem in generating Findment diagrams for it. For this. And now if you just want the 0th order term for free electrons, then I put a 0 here and a hat over there and a 0 here. Then what is this expression? Now let me just turn the crank with diagrams. Now I have two external vertices, a density vertex rho and a density vertex rho. So now the density operator, instead of being just a single line, the density operator, you may remember, was something like C dagger C, rho of Q, or C dagger K plus Q, CQ. So I just represent that by this circle where I have momentum Q coming in, and I create a particle momentum K plus Q and annihilate it with Q. So that's what the density operator, rather than having one external line, the density operator is equivalent to a particle whole line, a particle coming in and going out at this vertex. So this is my one density operator. This is the other density operator. And now I just connect them by the Green's functions. And so the 0th order density operator density correlation function in imaginary time is just given by this graph. And now I evaluate this graph by the rules. So what are the rules? First of all, in the definition of the density operator is a minus sign. Now this has a closed fermion loop, so I pick up another minus sign. So that minus sign is gone. And then I have a G0 here and a G0 here. And I just make sure I conserve frequency and momentum at every vertex, including this point. So if I'm sending in Q and omega, then and K here, then this must be K plus Q. So that gives me all these arguments. And then I sum over the internal momentum and frequency, and I get this expression. So the diagram rules in a few minutes allow me to write down this expression. Now I'm faced with evaluating the summation over epsilon. And depending on taste, depending on what you like to do, you could take this expression and then go back to our magic formula here and evaluate it using that. Or I take a more predictive. Every time I do contour integration, I'm guaranteed to make sign errors. So I just use the partial fraction trick. So it's just what you want to do is to take these two terms in the denominator and split them out. So here's only the first term, second term here, and this term over here with a difference. And now if I combine these two, I will get that with the denominator, with the numerator. I get the two terms in the denominator with the numerator, but then I divide out by the numerator. So this is exactly equal to this, just simple algebra. This is partial fraction decomposition. And the purpose of this is that all the epsilons are inside the summation, and the numerator that I had to cancel out is independent of epsilon. And that's the key thing. So then it's easy to do. And now each of these two terms is exactly the term that I had before. Now I don't have any convergence factors, so you might worry about that. Which convergence factors would I put in here and here? Well, in fact, you can put anything you want. The answer is independent. And so it's good to see why is it the convergence factor doesn't matter here, whereas it mattered over there. Well, the point is that why did we need a convergence factor? If we just go back and look at the original expression. If you look at this expression, forget the sum over Q. I'm just doing the sum over epsilon. And I'm doing the sum over epsilon, and I look at this expression. At large epsilon, it goes as 1 over epsilon. And something that's going as 1 over x is not integrable. It's divergent at dx over x. It diverges as the cutoff goes to infinity. It gets the logarithmic divergence. So there's a divergence here as in the summation as n goes to infinity because it's going as 1 over n. And then you control that divergence by this convergence factor, and then that tells you exactly how to control it in a sensible way. Point here is that if I look at this expression at large epsilon, there's a 1 over n here and a 1 over n here. It goes to 1 over n squared at large n. And you know that sum over n, 1 over n squared is perfectly convergent. So this thing is a perfectly well-defined expression with no divergences. I made the silly thing of introducing a divergence by doing the partial fraction. But so then I can control it if I want. But the thing is that even though individually the result of either of these two terms will be the same, no matter, depending on how I can roll the divergence, when I take the difference, it should all cancel out. Anyway, so if I want a convergence factor, I put in that convergence factor that I know how to deal with, exactly this, so that life is familiar. And then I can do the summation. One more, so there's one little twist we have to be careful about. The frequency here is epsilon, and the frequency here is epsilon n plus omega n. So now, since you're summing over frequency, you can change the dummy variable of integration. But another important thing to notice is that this rho is a bosonic operator with two fermions. So it has its frequency. This frequency here is not an odd multiple of pi t, it's an even multiple of pi t. So omega is an even frequency, not an odd frequency, whereas epsilon has to be an odd frequency. And luckily, epsilon plus omega, even plus odd, is still odd. This is still an odd frequency. So I can just absorb the omega into a shift of epsilon, no problem, because it's an even frequency. And then just do the summation. So you do the summation and you get this result. Okay, so that should start looking familiar to you. It's almost the Lindhardt expression. But the Lindhardt expression was in real frequencies, and it was obtained for the retarded commutator. This is just the time-ordered imaginary frequency object. So it's not what we wanted. Okay, so then finally, the last piece of the puzzle that tells you why diagrams are so useful is that we have to connect the imaginary time Green's function to the Kubo formula Green's function. These are mathematically totally different objects. Okay, and the key trick is the spectral representation. So we recall this about 2 or 3 lectures ago, I gave you the spectral representation. This is the exact expression for chi of k and omega. The actual Kubo for real frequencies omega was given by this this expression, where A of k omega, the spectral density, was given by this expression. Okay, so we derived this by putting in lots of complete sets of states, you know, over and over again, using the identity that sum on n and n equals 1. And we got this, that's all. It's just completely exact, in similar in spirit to the tricks we used for proving the KMS condition in the beginning of this lecture. So now I'm going to skip this. Now you do the same, you apply the same procedure to this expression. You take this expression, the time-ordered expression, and you put in complete sets of states here and out here, and manipulate it and do the integral. It's really straightforward. It's not something I want to, you know, it's in all the books, and just a few simple steps. And when you do it, lo and behold, you get this expression. So this is the Kubo formula expression for the commutator on the real frequency axis, the retarded commutator, because the integral over time was only for positive times. This is what's equal to, with an I8 of convergence factor that we had to put in. And this is the expression for the time-ordered correlation function on the imaginary frequency axis. And notice they're almost exactly the same. In fact, they're pieces of the same analytic function in the frequency space, because the numerator here, the spectral density, is exactly the same with no changes whatsoever. So basically, to go from chi of k and omega to chi of k and I omega n, the Matsubara frequency, which is omega n, no, that's the notation I've used. All you have to do is replace this omega plus I eta by I omega, where these are the Matsubara frequencies. And it has to remember that this actually only works at these Matsubara frequencies. At other frequencies, that expression is something else. That is this expression. I mean, this thing is only well defined when this is a even Matsubara frequency. Okay, so that's a very crucial and important result, that the spectral density of the retarded commutator is the same as the spectral density of the time-ordered correlation function of imaginary time. Now, even though this is a very suggestive expression, it's not so easy to implement, at least when you have numerical results. So, you know, what typically happens is that an experimentalist would do some experiment, some scattering experiment or something, and will measure A of k and omega. And a theorist will go and do some Monte Carlo simulation on some big computer, and the Monte Carlo summation is much easier to do, in fact, only really possible in imaginary time. And so the theorist will compute this object. Now, the theorist, having computed this object, would love to compare the results with the experimental measurement of this. And that's not easy to do. So it's because of what's called the inversion problem. So given chi of k and omega, can I compute A of k and omega? Well, it was no problem here. I just took the imaginary part when this was a real frequency. I just take the imaginary part of this object, that gives me this. You're done. But what the theorist has is not this thing, but it's really, I should to emphasize this. This is the complex frequency. Z is I omega n. So what the theorist has is information at these imaginary frequencies where there's no I eta here. This is just some number of order 1, nothing infinitesimal about it. So you have to then know this to figure out this. And that's not easy. Thousands of papers have written on the inversion problem. It's what's called an ill-posed problem, in the sense that a very large error in A of k omega ends up making only a tiny error on this. In fact, there could be exponentially huge error on this at large frequencies, and it'll only make a very tiny error on the Matsubara frequencies on the left-hand side. But nevertheless, people do it anyway, and many, many papers are written on that, using something called the maximal entropy tricks and many other tricks, which give you, so theorists have these results, and then you use a maxent method to get the most probable value of this. But there's no guarantee it's going to work. So that's one of the key things where, well, maybe quantum computers will someday measure this. That's why you need quantum simulation directly. Okay. So anyway, but when we're doing, when we have an expression like this, there's absolutely no problem. So as a theorist, I just computed this. And so how do I convert this to the physical correlation function? Well, here, since I have an analytic expression, all I got to do is just replace this by omega plus I eta, and I'm done. So therefore, if you really have an analytic expression in the complex plane, like we do at infinite number of points in the Matsubara axis, all I have to do is replace this by omega plus I eta, and I'm done. I get exactly the same expression. Now I get the Lindard expression. So obtained here by this summing this bubble diagram. Here's another picture of the whole issue. You can think of chi of k and z as some analytic function in the z plane. The diagrams give you the result for chi of k and z on these points, or if you're doing a numerical simulation. This is an even frequency, so there's even a point at 0 at omega n equals 2n pi t. What I would like to get for my comparing with some experimental scattering data is chi of k and omega over here on the just above the real axis, omega plus I eta. So I have to analytically continue from here to there. And that whole analytic continuation is not so easy if you only have numerical data. If you have an analytic expression, then you can use your knowledge of complex variables to do it exactly. Another important point worth mentioning here in the complex structure of this density response function, that this, if I now define, chi of k and z is defined to be the following function in the complex plane. Is defined to be d omega over pi a of k and omega and omega minus z. So the so-called Hilbert. So for any complex z, I can work this out. And what you notice is that for the frequencies omega, for which a is non-zero, let's assume it's true for all frequencies. Well, for the up to 2kf, it's true, right? What you see then is that there's a discontinuity in the imaginary part, because on the top of the free axis, you'll have omega plus I eta. In the bottom, you'll have omega minus I eta. And that flips the signs of the delta function. So in fact, you have a branch cut or in some cases poles if you have a finite system like an atom, on the real axis, corresponding to, and the discontinuity of the branch guard is the imaginary part of A and K omega. Okay, that's probably more than you need to know, but just to get everything down, that's how imaginary time functions, which theorists love to compute and are much easier to compute by a computer, ultimately have to be related to actual physical response functions, which are measured at real frequencies, not imaginary frequencies, and they don't involve time ordering. Remember the Kubo formula had no time ordering; it was just the commutator. And there's this very beautiful relation, I don't know who discovered it first, between a time-ordered correlation on this axis. So what we're computing is the time-ordered correlation function on this axis, and the commutator on this axis. All right. Now, so something's a bit confusing because in particle physics, there's other sets of Green's functions you define, and even those on the imaginary axis. But typically they work at 0 temperature. And what particle physicists define in the I8F prescription, for the ones those of you who have taken field theory, is a Green's function that's not on, so what we're talking about is a Green's function just above the real frequency axis. That's the Kubo formula. And the particle physics Green's function, sometimes called the Findment Green's function, is below the real axis for negative frequencies and above the real axis for positive frequencies. So, that's obviously connected by some other spectral representation. In fact, they can all be reconstructed if you work hard enough from the same A of K and omega with somewhat different contours of integration. So, for the retarded commutator, you integrate over here, and for the others, you integrate like this. Anyway, it can get very confusing, and I never get it straight. I'm just telling you the one that I'm most familiar with, which is what condensed matter physicists use. But it is difficult to translate the language sometimes, because historically these were developed, and the needs are very different, and they were developed for different purposes, and these are what we find most useful, because we are typically dealing with a system which is at finite temperature and in our thermal equilibrium. All right, questions? Okay, so now we have done everything we did before, and we want to do more. So let's get started, at least in this lecture. So finally, we are done with the introduction to diagrams, the whole technology of diagrams, and we've satisfied ourselves that we can reproduce everything that we knew. Yeah, everybody clear on that? Are there further questions on that point? All right, so let's put this to some use, to something better. Okay, so remember we had introduced something called a dielectric constant, epsilon of K and Q and omega, that was defined as a renormalization of the interaction V of Q due to the presence of the electron gas. You put in 2 test charges, and then you looked at the interaction between them, and we found that it was screened because of the electron gas moving around and screening the interaction between the 2 test charges. So we can now take a diagrammatic point of view. We just imagine that there's some test charge sitting here and a test charge sitting here, and now we put in some interaction between them. Okay, so we just draw all possible diagram with 2 external interaction vertices. Okay, so there's not a Green's function. That's all it is. Then you have some test charges, and there's some interaction between them. So pretty soon, you start thinking in terms of these diagrams. It's very intuitive. All right, so you got to put all diagrams with 2 external interaction lines. So this is the simplest one. You just connect them up. but then these are some of the others. And as we'll see in a minute, these, in fact, we already accounted for in a chapter on screening and plasmons, but you can get more complicated stuff like this. All right, so there's lots and lots of such diagrams that we have to sum to figure out what the dielectric constant is. Okay, and I don't have to write a single equation, just do it in pictures. Right. Yeah, okay. So now we're going to use a trick rather similar to Dyson's trick for the electron Green's function. And we'll see what that relates to. So what we're going to say is that if I look at these diagrams, again, I see some are different from the others. There are some that fall apart when I cut an interaction line, not a particle line, interaction line. So these are one interaction reducible, whereas this one is not. This one, if I cut an internal interaction line, doesn't fall apart. So let me introduce something called a blob for now, which is the sum. What is the blob? Is the sum of one photon. So let's imagine the interaction is really a photon, which is what it would be in field theory if you had relativistic effects. Sum of one photon irreducible graph. So all of these graphs here, like this, and this, and many others, I'm going to call as, so that, this leading order term is just chi0, the free, that's exactly what we evaluated a minute ago. That's this thing that we call chi0. So the sum of all of these graphs, or sum of all these blobs, one blob, which includes all one particle irreducible, one photon irreducible graphs, not one electron irreducible, I'm going to call chi irreducible. Great, something in general. Okay, so then the analog of Dyson's equation is that the exact expression for this is equal to, I haven't even written it. Yeah, is equal to this. So the exact expression for this is exactly this geometric series. I have V, then I have V, chi irreducible V, V, chi irreducible V, chi irreducible V, and there's nothing else. You might say, well, what if I put a line from here to there? Well, putting a line from here to there produces a diagram that's actually part of chi irreducible, because there is another term here in the dot, 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 something like this. This term that's included in chi irreducible, because this is not reducible. If I cut one photon line, it still doesn't fall apart. Okay, so this is an exact expression. It's a geometric series, no problem. I can sum the geometric series, and therefore I conclude that V of Q over epsilon of Q and omega is V of Q times is sum of this series, and that's the usual geometric series. It's the first term times 1 minus the ratio, and that gives you V of Q times chi irreducible. So this V of Q cancels with that, and I get an expression for the dielectric constant. This is an exact expression for the dielectric constant. The dielectric constant is 1 minus V of Q times chi irreducible. Okay. So this is the exact expression, and all I have to do now is compute chi irreducible, at least. But what did we do before? We replaced chi irreducible by just this graph. So the RPA theory, chi irreducible is approximately equal to this. I should make that approximate, and equal to chi naught. So that's chi irreducible in the RPA approximation. So beyond RPA, if I want to correct RPA, but previously I had no clue how to do it, I have to now include these other terms. And in fact, some of these terms we can reduce. There's many others that I haven't written down. There are all kinds of more complicated ones like this, or the one that I drew over here, like this one. These are all part of chi irreducible. and then there's things like this, and so on and so forth. I've just drawn some of the higher, in fact, these even have names, and people have studied a lot of these things. This is called Markey-Thompson, this is called Aslamazov-Larkin. You know, that's a whole project, and we're not going to discuss them in any detail here, but there's some corrections. All these graphs here are corrections to the RPA theory. We're going to just look at some of them. In fact, the ones I drew in black, the so-called ladder diagrams. And that's relatively easy to evaluate, which I'll do next time then. Okay, so the basic lesson is that, you know, RPA and screening and plasmons, they all come about from just summing, you know, these graphs. This is RPA. So the Debye theory of screening, that's just summing these graphs. So it has repeated interaction. It's not first order in V. It's got interaction to all orders, but it's the same sort of interaction over and over again. And mean field theory and Hartree-Fock, they all have the same flavor of just summing the basic interaction over and over again. But then, you know, this is the kind of thing we haven't considered yet. And that'll be next lecture. So the next lecture won't be on Monday. Monday is a wellness day, if I got it right. So that will be on Wednesday. The other announcement is we have another TA for the course since the enrollment is larger than expected. Darshan Joshi, he is also available for office hours. I think he'll be contacting you or will announce his office hours, and we'll be doing the grading. He won't be taking sections though, like Ryan is doing, and so feel free to contact him also. Further questions? All right, well, I assume someone's out there listening and or watching the recording. I'll have a discussion session tomorrow morning at 9 a.m. That's the program, and we're happy to discuss more of this tomorrow. Okay, see you tomorrow morning, and then the next lecture will be on Wednesday.